Portion of our breakout sessions. My name is Shane Mott. I'm with Rutgers University Cates, and I'm going to be moderating today's sessions. So the first one we have is by Dr. Hao Wang. He is a professor at Rutgers University in the Civil Engineering Department. Presenting will be Xiao Chen. He is a PhD student, and he is the one leading the research for this particular project. And Xiao, whenever you're ready.
Good afternoon, everyone. My name is Xiao Chen. I'm a PhD student from Rutgers University, and my advisor is Professor Hao Wang, and he is also a graduate director in our department. I was thinking maybe I will present in a small room, but this one is actually in XXL size. So my presentation topic is asphalt pavement pothole repair with recycled material and preheating. This study is actually the latest updates of almost finished project with NJDOT. So here's a quick background. As we all know, the pothole is a bowl-shaped depression on pavement surface that affects the pavement deterioration and traffic safety. Especially when we're driving on the highway, the pothole may make the vehicle have some damage or make the passengers feel uncomfortable. They are usually caused by water infiltration through surface cracks and freezing soil cycles. The primary failure modes of the failure of asphalt patch, including the surface rutting, interface debonding, and raveling. And repairing them has been one of the most important and frequent maintenance activities for highway agencies. And currently, hot mix asphalt is the most widely used patching material, and the throw-and-go method is the most commonly used procedure. Although some DOT will use spray injection method to do the patch, but based on our survey responses, the cleaning could be an issue for the spray injection equipment. So most DOT still prefer using throw-and-go method. They will use either the back of the shovel or a steel tamper or even the trap tires to do the compaction. And in our previous work in this project, we have evaluated the feasibility of preheating method in pothole repair, and we proved that preheating can improve the performance of the asphalt patch. Therefore, in this study, we are trying to see if we can add in some recycled material to asphalt patch, and then we can achieve some environmental benefits. But certainly, wrap material has some durability issues and might be very sensitive to moisture. So we will still introduce preheating method here, and we want to see in the combination of wrap and preheating, can we achieve some environmental benefits without significantly impact the performance of the patch. So this study includes two parts. First part is evaluate the performance of HMA with different wrap content through laboratory experiments. And then we will select the most appropriate content and adding them to the new HMA as the patching material for field evaluation. And the second part is evaluate the in situ strength of the repaired pothole with the field course, and then we quantify the benefits of this repair quality. And in the laboratory, we made the patching material using new HMA and recycled asphalt pavement. The new HMA has a 9.5 millimeter maximum nominal aggregate size, and the asphalt binder performance grade was 64-22. The HMA was collected from the asphalt mixing plant, and the recycled asphalt pavement was milled from different pavements. The first picture shows the appearance of the wrap material, and the second one was the gradation. And instead of gyratory specimens, we made Marshall specimens because of the large amounts of samples we need and the limited material we have. We made 4 groups of specimens. We have control HMA, and we have HMA with 15, 30, and 50% of wrap. And we selected 3 different mechanical testing to evaluate the performance of the patching material based on the primary failure modes. So we did indirect tensile strength test to evaluate the rutting resistance of the patching material. And we did interface shear strength test to evaluate the interface bonding condition. And we did the countable test to evaluate the abrasion resistance. And because the wrap material may have some moisture sensitivity, and also based on our survey response, the water is the main reason for causing the pothole failure. So before we doing the mechanical testing, we put the specimen under 2 different environments related to the moisture. The first is freezing thaw. So basically we put samples under -20 degrees C for 24 hours, and then put them under the water bath with 60 Celsius, and then for another 24 hours, and then we do test. The second environmental conditioning is we loaded some dynamic pore water pressure on the specimens using a device called moisture-induced stress tester, which is also called MIST. So basically, we can see from these 2 pictures, basically we put the Marshall specimens in this cylindrical chamber, and then we filled with hot water and sealed it. And there's a blade inside which can inflate and shrink to apply the pore water pressure. And based on the standard, the magnitude of the pressure was around 280 kilopascal, and the temperature of the water was 60 degrees C. And we totally applied 3,500 cycles for each conditioning. And this slide shows the IDT strength of the lab specimen. We can see that as the wrap content increased, the IDT strength of patching material increased under dry and freezing thaw conditioning. This is understandable because the wrap material was coated with very aged binder, and the wrap was stiffer than the new HMA. However, under the mist conditioning, we found the IDT strength decreased with the wrap, probably because of the negative impact of the hydraulic scalding effect. And from the strength ratio point of view, as the wrap content increased, the IDT strength was less resistant to the moisture, especially freezing thaw. And for the interface shear strength, interestingly, we didn't find a significant impact of the wrap on the interface bonding. The reason we guess is because when we mixing the wrap with the new HMA, the actual wrap material distributed exactly on that interface was random and unknown, which could be a possible reason. And similar as the IDT strength, we found that the impact of freezing thaw was more significant than pore water pressure on the interface bonding condition. And then we measure the mass loss of the lab specimens after conducting the current ball test. And the results are very straightforward. As the wrap content increased, mass loss increased regardless of the conditioning environment. But different from IDT and the interface condition, we found the mist conditioning is more significant than freezing thaw for the abrasion loss. And then we decided to use 30% wrap for field evaluation because the freezing thaw condition, the tensile strain ratio value of the HMA with 30% wrap meets the minimum requirement of 70% from the AASHTO standard. And also the mist condition, the tensile strain ratio of this new patching material meets the recommendation of 80% proposed by other researchers. And additionally, the interface bonding condition and the abrasion resistance of this new patching material was close to the HMA without wrap. So we decided to add 30% wrap to the new HMA as the new patching material for further field evaluation. And in the field, we had a test section at Rutgers campus. We built it like 2 years ago, also for this project. The test section was constructed in 2 layers, 3.5 inch plus 2.5 inch. And the construction material was the same as the HMA in our patching material. And we made some artificial potholes during the construction. So basically, after paving the bottom layer, we put some wood blocks on it, and then we directly paving the top layer. And after paving, we removed the wood blocks immediately. And after cooling down, we have these artificial potholes. And for each pothole, it was around 30 centimeter long, 13 centimeter wide, and 6.2 centimeter thick. And based on our previous study in this project, we have evaluated the heating performance, as I just mentioned. So based on that results, we applied 5 minutes of preheating here. We used a portable infrared heater, and its power was around 4,300 watts. And if we look at the second picture, after heating for 5 minutes, the temperature of the bottom of asphalt puddle would be around 100 degrees C, and the edges was up to 160. So which means a good heating performance. And then we do a compaction using a factory plate comparator for 10 seconds. Initially, we also tried using a steel tamper to do the compaction based on the current standard from NJDOT. But it turns out that we cannot get intact field core because of the torsion from the drilling machine. We found that the field cores were damaged after drilling. So we think maybe the steel tamper cannot ensure good compaction quality. So in that case, we cannot get field cores for further mechanical testing. And then we decided to use the factory plate compaction. And as shown in the first picture, we took 2 field cores within the asphalt patch area. So in this case, we can get 2 field cores with the horizontal interface between the patch and the old pavement. And we also take another 2 field cores at the edge. So in this case, we can get 2 field cores have that vertical interface between patching and the old pavement. And if we look at the last picture, it was the patching material have the vertical interface. And even with the factory compaction, we still observed some damage during the drilling. So almost all of the patching material detached from the old pavement at the horizontal interface. So we decided to do the IDT and the countable test on those detached patching material because they are pure patching material. And then we did the interface tensile strength on the patching material with the vertical interface. And based on the previous lab testing, we found that the freezing soil conditioning is more critical for IDT and interface condition, and the mist conditioning is more critical for the abrasion resistance. So similarly, in the mechanical testing of the field cores, we applied the freezing soil for IDT and the interface and applied mist conditioning for the countable test. And here is the results of the IDT strength of field cores. We found that the IDT strength increased under both dry and freezing soil conditioning if we applied preheating. This actually verifies the positive effect of the preheating method. And from strength ratio point of view, although the HMA with 30% wrap has the lowest tensile strength ratio, which means the poor moisture sensitivity, however, when we apply the preheating, the tensile strength ratio increased and becomes comparable with that of the pure HMA. This indicates the potential of using wrap material in puddle repair, but we still need to evaluate the interface and also the abrasion resistance. And here is the interface tensile strength of field cores. We found that without preheating, the asphalt patching material with wrap material failed after freezing soil conditioning. Even before we doing the mechanical testing, it was failed because of the freezing soil. And when we applied preheating, the field cores was still intact after freezing soil conditioning. And we can measure the interface bonding condition, and we found the preheating can enhance the interface bonding condition and both dry and the freezing soil conditioning. And from strength ratio perspective, when preheating was performed, the moisture sensitivity of this new patching material was similar with that of the HMA without wrap or preheating. And finally, we measured the mass loss of the field cores. From these 2 pictures, we found that the addition of the wrap led to high mass loss and increased moisture sensitivity, which is expected. However, after we apply the preheating can mitigate its negative impact and lead to a comparable abrasion resistance with pure HMA. And here are the conclusions of this study. From the both laboratory and the field evaluation in this study, again, we verified the positive effect of the preheating, and we found that the preheating can not only enhance the interface bonding condition, but also the cohesive strength of the patching material itself. And although the abrasion loss, IDT strength, and the interface bonding of the patching material was less resistant to moisture as the wrap content increased, after we adding 30% wrap, the overall performance is still satisfactory as compared to HMA. This actually verifies the feasibility of using the combination of wrap material and the preheating in asphalt puddle repair without significantly impact the performance. And also, we think it is necessary to conduct further field evaluation on real in-service pavement using a simple compaction method to validate the findings in this study. And that's all about my presentation. And finally, we would like to thank for the technical project panel at the New Jersey Department of Transportation, and also thank for the support from Dr. Thomas Burnett and the staff at the Rogers Kate Asphalt Lab. That's all. Thank you. Do you have any questions? Okay. Thank you.
Yeah, if you have any questions, I believe these two microphones are working. If you want to come up to the microphone. If not, just raise your hand. But yeah, come up to the microphone.
Maybe I missed it, but did you compare, say, for a scenario for, like, say, typical pothole repair, if you use the preheating with 30% wrap, how's the cost of that compared to, say, just HMA? The cost comparison.
We
If you
believe
use HMA plus 30% wrap versus just a typical HMA.
we use the typical HMA, and then we replace part of the HMA with the wrap material, and then we mix them directly as a new patching material.
And what's the cost of these two methods, like the standard conventional HMA versus the HMA plus 30% wrap? The cost of that in a typical application of, say, pothole repair.
We did not do exact calculation for the cost, but we believe for sure that when we use wrap, we can reduce the cost and also achieve some environmental benefits.
Okay. Another question, right? Because pothole repair is such a it's just dominant issue, right? It's really like not an issue, but it's really an issue. How do you to disregard the cost? How would you think, say, if you use preheating with HMA, it's gonna be better than what we do with the cold patch, right?
Yeah.
Because pothole repairs, like I'm seeing on my street, they come, then they put it in, then a few days later, just a few weeks later, just fell out. So, if you just use preheating plus HMA, would you think that would outperform the preheating with HMA plus 30% wrap? I know we're not getting any environmental benefit here, right? By using that, that's a big part of it. But would you say, like, say, preheating, the preheating methods plus HMA be better than outperform the preheating plus HMA plus with 30% wrap?
Yeah, I would say yes. But our goal is to compare preheating with wrap material
I
to
know.
pure HMA without preheating. That's the current practice.
Yeah, I know. Okay. All right, thank you.
A few comments. Thanks for the question. Actually, the preheating mainly because of the product.
Are you guys doing this testing sort of in the lab environment, or it's like a real?
That's why also ideally is we put the repair on the field, but in this case, basically, we can do visual evaluation. So actually, real pothole can be any United shape.
Yeah.
So in that case, previous study also from other states, they just do repair with different layers and then observe for 2 years, 3 years. So in this case, we try to see use 5 years actually, the rectangular. But in this case, we'll be able to take a course to do the test. And then if you prove this brings benefit, and then we can bring the field for more like long-term performance.
What is your estimate? I'm sorry, I'm just making this like more, like in your professional opinion, your estimate. Do you see this, say, preheating plus HMA with 30% of wrap really come to be massively used? Do you see that coming? And if so, when do you see it coming to Jersey?
I see it as an advantage, but it do have one kind of disadvantage, that's the time. So you expect the field to increasing a few minutes for 1 hour. That would the actually advantage. So actually, that's something we are trying to see. Maybe this not apply to all the conditions. For example, if we repair at a very high traffic corridor, the crew will not be able to stay in this environment for a few minutes.
Yeah.
But if there's no like high traffic or something, we have as the freedom or the environment workout, it's definitely better.
Yeah.
So that's something when we get the conclusion, we talk with the actual chemists pretty field, one and it's through we talk with the really the person who doing the follow up, and he bring this concern that okay, yeah, it's good, but you want me to stay in that environment a few more minutes. Sometimes I'm not willing to. So that's something we want to consider. We really want to review planning.
Did you guys do this in conjunction with the DOT maintenance? Or sort of like okay, all right.
This immediately customer and.
So they'll have the biggest input in as regards to say whether or how to implement it, right? Okay, right. Thank you. Sorry.
Thank you.
The next presentation will be by Dr. Matthew Adams. He is a professor at the New Jersey Institute of Technology, and the presentation will be on the development and analysis of low embodied carbon concrete mixtures for use in transportation applications. All right.
Hi, thanks for having me. I'm going to talk about sort of the technical side of low carbon concrete today and some of the work that we've been doing. But this topic is really sort of snowballing very quickly, not just in the technical side, but also on the policy side. We've seen a recent law passed here in New Jersey trying to incentivize low carbon concrete. New York State just put out rules saying that concrete has to meet certain low carbon bench lines. The Inflation Reduction Act is having requirements for government funded concrete to meet certain carbon benchmarks. So this is really kind of coming down the line, whether we want to embrace it or not. The policy is moving ahead of where a lot of our concrete companies are, and so it's coming along very quickly. So I want to talk about some work that we've done with my colleague, Dr. Bandel, who's also a professor, and our PhD student, Yan Zhang. This was also a collaboration with Rutgers and Princeton. So working with Dr. Wang's group at Rutgers and Dr. Moini's group at Princeton. So just to kind of set the background, concrete is a large producer of CO2. It has a lot of embodied carbon within it. It's responsible for about 8% of the total anthropogenic carbon emissions in the world. And that can be compared to the entire building materials and construction sector, which accounts for 11%. So concrete makes up the majority of that concrete production. And so where is all of this coming from? The reality is concrete has a relatively low embodied carbon per unit volume. So 1 cubic meter of concrete has a pretty low embodied carbon compared to 1 cubic meter of, say, steel. But the amount of concrete that we make every year is just so massive that it has a really outsized impact on the world. Here in the US, we make over 400 million cubic yards of concrete, which is the equivalent of over 600 Hoover dams being cast every year in the US. So that's just a massive amount of material. And we're not likely to get away from making that much concrete anytime soon. We don't really have a viable replacement material on the near horizon. So we need to figure out how to work with that. So where within concrete is most of that carbon coming from? Over 90% of it is associated with the production of Portland cement, which is part of the concrete mixture. And when you make Portland cement, you can actually attribute most of the emissions, the carbon emissions, to what we call process emissions, which is part of the chemical changes that happen when you go to take your raw materials and turn them into cement. The rest of the carbon, the other 50%, comes from the process to ship it and grind it, and then the process to heat up your kiln. So this research was performed for the Port Authority, and they have some really ambitious goals for meeting the Paris Climate Agreements, for reducing their overall greenhouse gas emissions across the agency. This program was focused specifically on concrete, but they are also, a national leader in terms of green and sustainable construction. And so we were engaged to help them really define what tools in the concrete mixture toolbox they wanted to use and focus on moving forward. So this project originally consisted of 4 main tasks. Task A was to analyze and calculate the current state of embodied carbon in the Port Authority. This is the work that Dr. Wang's group at Rutgers mainly focused on in the initial work. Task B was to develop and propose the concrete mixtures that we should test. Task C was when we actually did the laboratory testing, and Task D is field performance monitoring. So we're currently starting up Task D, and we're about to cast some field concrete to do long-term monitoring of selected mixtures from Task C. But today I really want to focus on Task B and Task C, so developing the concrete mixtures and the laboratory testing. So Task B, which was our development phase, had the main objective of proposing 20 low embodied carbon concrete mixtures to the Port Authority that we could use for testing in the lab to see how they could perform in laboratory tests and what their embodied carbon or global warming potential would be. And one of the key parts of this is that technologies really had to be market ready. There's a lot of great technologies on the horizon coming through research, but so many of them are just in startup phases, not available widely. So we really focused on what can we do today and maybe in the next 5 years rather than what's coming in 10 or 15 years. And so our methodology here was really to focus on the key areas where we can improve based off of the analysis from Task A. From that, we studied ways that we can improve performance using aggregates, and ways that we can perform it using cementitious materials, and then we developed our mixtures and proposed those to the Port Authority. So we really broke this up into a few groups of technologies. The first group was to focus on supplementary cementitious material usage, so increasing the amount of cement that we are replacing in the mixture with other lower carbon materials. So newer technologies like ground glass pozzolan, trying to understand how Portland limestone cement might affect the system, and then really looking to push the boundaries of how much of these materials we could put into the concrete. We also looked at optimizing our mixtures to reduce the total Portland cement in the mixture, so improving the amount of aggregate in the system, and also looking at CO2 carbonate seeding in the system. And then we also looked at using recycled aggregates as well. So when we were looking to create these mixture designs, we went through a process of a literature review, which we basically pulled out many different mixture designs from literature based around a certain topic. So these are all mixture designs that have fly ash. They're rated by the compressive strength at 28 days. We were looking for a system that had 4,000 to 5,000 PSI at least. The water to cement ratio, we wanted at least systems that had around a 0.4 water to cement ratio. And then we wanted total Portland cement content to be less than 400 pounds per cubic yard. From that, we chose some example mixtures that we wanted to keep as like our target, and then using our own materials at home, we developed some new mixtures to push that boundary. When it comes to the work with trying to reduce cement, the total cement content, cementitious materials content, we focused on optimizing aggregate gradations through particle packing. This is the work that was mostly done by Dr. Moini's group at Rutgers, or at Princeton rather. And what we were able to do was take specific aggregates and run some testing to figure out essentially what's the highest percentage of void space that we can fill with aggregates before systems become too difficult to work with. So for example, these two aggregates, we were able to get a 77% void space filling with just two aggregates, but when we moved up and included a third aggregate, we were able to improve that by another 0.5%. So that's all space that we were not having to put cement in. We then used coarseness factor charts to determine sort of what the workability of the systems would be with these aggregates. And we were able to choose the right blend of aggregates to increase our total packing without significantly reducing workability. So we saw maybe 5 to 6% increase in total volume of aggregates over standard mixtures that were already being used, which is, quite a bit in terms of reducing cement content. With all of that work, we came up with 20 different mixtures that had relatively lower global warming potential than their sort of average Portland cement mixture, which is all the way there on the left. So these are just the broad range of different systems that we use. So we were looking at systems with fly ash, with slag, and very high percentages of slag. So we actually did some mixes with slag at 77% replacement. Ground glass pozzolan, some ternary blend systems where we used both slag and fly ash, or ground glass pozzolan and slag. And then also they wanted us to look at some rapid repair systems, so we looked at a CSA as well. So that brought us to task C, where we wanted to study the performance of these mixtures in the laboratory, so that we could sort of assess the suitability of them in the lab for potential use in the field. And from this, we could then recommend potential mixtures for the pilot system. So our process here was to cast our trial mixtures based off of those final mixture designs, or we cast them to finalize our mixture designs. We had to do a lot of work with admixture replacement levels and air entrainment levels, things like that, because all of that is very finicky. You can't, those admixtures are so finicky depending on temperature and your exact materials, so that took a little while. And then once we figured those out, we cast our finalized mixtures. We measured fresh properties, so focusing on workability, setting time, and air content. And then we measured our hardened properties, so strength, of course, freeze-thaw performance, shrinkage performance, and permeability performance. And then we analyzed all of those results to come up with potential systems for field testing. And this was actually ended up being quite a bit of concrete. We cast probably around 20 cubic feet of concrete in the lab for each one of our mixtures. And when you have a concrete mixture that can only mix about 3 cubic feet at a time, this is actually a lot of concrete made in our lab. So just an example of some of how we did some of our analysis in terms of how systems performed. This graph shows the initial setting time in green and final setting time in black of the different concrete mixtures. We set upper and lower quality limits, so that's what these red lines are. So for setting time, our lower quality limit was our upper quality limit was a 3.5 hour initial setting time. So we wanted at least a 3.5 hours for initial working time before you got to that initial set where you really couldn't do your finishing procedures well anymore. And then we didn't want our final set to happen any longer than 10 hours, right? Preferably lower than that, but this was sort of the max level that we were willing to accept for certain mixtures. For the most part, all of our mixtures were able to meet these requirements. Surprisingly, even our 77% slag was well within these requirements, especially with the longer, the final set time. And that had our highest amount of SCM, which typically slows down your setting. But this gives us a good idea of how much working time we'll have in the field and potentially how long it will take before we can strip molds and start doing other work on the concrete. Here's an example of our mechanical performance. This is our compressive strength. So we looked at compressive strength over 180 days. All of our systems had a minimum of 4,000 PSI. That was sort of our minimum requirement for strength at 28 days. All of them met that or exceeded it. And in some cases, we actually had 56 and 180-day strengths up above 11,000 PSI for a mixture with less than 400 pounds per cubic yard of Portland cement. So we actually got great strength results out of these systems. Our biggest issues were with our optimized aggregate systems, and this is sort of a technology that we need to dive into a little bit more to understand how to better design those mixtures in terms of strength. But overall, we did pretty well. We also looked at durability performance. So this is rapid chloride penetration testing. If you're familiar with that test, you pass a charge through a chunk of concrete, and based off of the amount of charge passed, you can have a rough idea of how resistant it is to chlorides moving through it that may cause corrosion. So we have a lower quality limit, meaning that in order for it to be acceptable, it couldn't pass more than 1,200 coulombs of charge. This one was not quite as successful with all of our mixtures as some of the other ones, but we still got fairly good performance across the systems. Typically, when you use supplementary cementitious materials, these will densify the system, and so you do expect better performance in the rapid chloride penetration test when you use those materials. So we sort of expected some of these results, but it was good to get a double check on that. So in the interest of time, I'm not going to show all of the results, but this table basically summarizes our results for all of our mixtures. We have all of our performance metrics on the left. Our mixtures are across the top. And basically, the closer to dark green you get, the better the systems perform. So our 77% slag mixture, the mixture that had the highest amount of SCMs, actually is the only one that met all of the criteria for performance, which was actually surprising to us because, that can be, that there's some, traditionally some beliefs that there's too many challenges when you move that high in terms of strength and setting time, that we wouldn't be able to meet this, but it performed really well. And then we had a number of mixtures that met at least 6 out of the 7 criteria. So that kind of gave us our baseline for which mixtures we wanted to start to analyze for doing field testing. We're still finalizing which ones we want to do, but certainly that 77% slag is going to be in the mix. Our next step is going to be our pilot program. I stole these pictures from Rutgers' website. They're not mine. Basically, we're going to do 3 different field trials of tested mixtures. It's all going to be exterior concrete that's exposed to de-icing salts, exposed to freeze-thaw cycles. We're going to do long-term monitoring of these systems. So we'll do crack mapping, look at scaling and delaminations, and also corrosion in these systems. We're also going to take companion samples back to the lab from the actual mixes from the concrete trucks and run the same lab tests on those to make sure that the stuff that's coming out of the truck is giving us similar to performance to the stuff that we made in the laboratory. And so hopefully we see similar performance in the field as to what we did in the laboratory. Of course, scaling up mixtures is a whole new challenge from just developing them in the laboratory, but we're really excited to see how these low carbon concrete mixtures perform. And we're able to actually, some of the mixtures that we're looking at, we're actually reducing the average embodied carbon or global warming potential of the concrete over the Port Authority's average by about 50 to 55%. So we're seeing really incredible potential in terms of reducing the carbon emissions for these concrete mixtures. So I just want to acknowledge, of course, all of the people that worked on this project. This has been a fairly large project, teaming up with Rutgers and Princeton, and the groups who gave us some funding to do the various parts of this project, and our material suppliers that gave us some samples for this. So with that, thank you for listening to my talk, and I'm happy to take any questions.
The test results on high early strength concrete where you're able to split the forms within like 24 hours and still meet all the criteria, including the permeability?
So we ran 3-day testing. We didn't do 1-day testing because that wasn't, we were not doing a high early strength process with this. The client was more interested in sort of normal strength concrete. High early strength is a whole other beast that needs to be tackled as well in terms of low carbon emissions, because people tend to boost the cement content in them to get that high early strength. But that's a whole other research project.
Thank you. Is this concrete, you can pump that one that met all your criteria, that can be pumped?
We didn't do any pump testing for this. This was all in the lab, and we don't have a pump in our lab. So that's hopefully going to be part of the field trials, is looking at the actual field workability coming out of the truck and what we can do with it.
Wet cured? For a concrete deck, would it have to be wet cured?
Oh yeah, I mean, all of this would have to be wet cured or good compounds. I mean, with any concrete, it should be wet cured.
Thank you.
Oh, I know a lot of this is like preliminary mixes still, but you guys have like a ballpark effect of the changing costs to switch to any of these mixes?
So, most of the materials that we're using are already on the market, and they're selling for relatively they're not having major cost impacts on the cost of concrete. So, most SCMs are selling for roughly the same price as cement. Initially, people trying to implement these, there's probably a cost increase just associated with learning how to do this, some additional testing, et cetera. But long term, the cost shouldn't be very different with the ones that we tested. We had a handful of mixes with fly ash. We had a bunch with slag. We had some with ground glass pozzolan. We had some with Portland limestone cement. So, locally, fly ash is hit or miss on whether it's available, depending on your supplier. The actual production of fly ash is reducing, but there's a lot of fly ash that is in various storage ponds around the U.S., and research is showing that it's all very capable of being used as fly ash in concrete. This was a type F that we used. Yeah, so so this is our GWP per our original proposed mixtures. So you can see kind of what the GWP might be for the various systems that we did. Yes, so these include some emissions, some emission costs associated with fly ash and slag. What we used for that was essentially a cost balance, or a profit balance on those. So if we assume the company makes money off of selling the fly ash, so we allocated some of the emissions to the production of the fly ash, which is, yeah, I mean, it's controversial whether you should do that or not. There's a lot of debate in the field, but we chose to do that. Well, I mean, if we didn't do that, the emissions would probably be lower. So this is a more conservative view of the emissions associated with the fly ash and slag.
And how we are planning on that concrete with the road that film with the binder.
Right. Yeah, so basically thank you very much.
The third and final presentation of our infrastructure breakout sessions. Today's presenter will be Manuel Celaya, and he is going to be presenting on the rapid assessment of infrastructure using NDT methods. Manuel.
All right. Good afternoon, everybody. So I'm going to be talking about a rapid assessment of infrastructure using non-destructive testing methods. As you may be aware, according to the ASCE report card, the most recent one from 2021, we don't have a good overall score. I think the score is a C minus on average. For roads, particularly, we're on the D range, which is poor. Bridges is a little bit better, it scores as a C, and public transit is at the D minus. No? So this presents a problem for public safety and also potential consequences of failure. No? Also, maintenance backlogs for all agencies continue to be an issue. No? There are a lot of roads, bridges, you name it, every kind of infrastructure needs more money and maintenance. And there are better practices of asset management, no? To prioritize and do a better usage of this limited funding. However, in order to implement this type of asset management practices, we need condition information or accurate inventory of our infrastructure. The inventory or condition assessment of infrastructure is mostly or has been mostly been done doing traditional inspection. This could be like visual inspection methods or methods that rely or they were based on the experience of the inspector skills and other factors. No, for example, if you need to do a bridge deck inspection, hammer sounding or chain drag was the typical method that is still being used. Or for example, for roadway assessment, it was done through either boots on the ground inspections or windshield inspections. Somebody driving with a vehicle and just riding the roadway. No, this type of traditional inspections, I mean, they have some problems with accuracy and reliability, and in many cases you could get variable results. No, some of these, because you need to have inspectors or engineers on the ground, they needed maintenance and protection of traffic, like lane closures, or you name it. So you're putting people at risk. So the objective is to minimize this risk and also obtain better data, no, from this, from all the from inspections. So we like non-destructive testing methods because they test the material in situ. It is safer because in many cases, or most of the cases, you need less people on the ground. Many of these inspections can be done with different technologies, but it can be done safely from inspection vehicles. They can provide a lot of better in-depth condition assessment and performance monitoring. And you also reduce dependency on the inspector's judgment of experience. No? Something that, even though I like, I've been working with NDTs for many years, something that is always, and I always recommend to do it, is always include some sort of ground truth testing. Besides what you get from whatever type of technology, I will get into that. it's always good to have like some sort of comparison with ground truth methods. For example, taking a core if you're measuring pavement thickness, or doing a visual assessment on a limited area instead of doing like a full bridge. So it's always that I always recommend to implement besides doing the whatever NDT method that you're looking for. These are some of the NDT methods that are out there. These are, some of them are not the state of the art, are already a state of the practice. I'm just naming some, I'm gonna present some of them, which I think are the most valuable, and they can do rapid assessment of different types of infrastructure. And I'm gonna be just briefly talking about the GPR, ground penetrating radar, laser scanner systems, LiDAR, 3D laser cameras for different applications, infrared thermography, and other NDTs like profilers, falling weight deflectometers, skid testing, and seismic ultrasonic testing. GPR is, I think, is probably maybe the most well technology that is out there for infrastructure assessment. It can provide a great coverage area. Usually it's done from a vehicle, so you don't need any MPT because the data is usually collected at posted speeds. But we also need, in some cases, like parking lots or areas with limited access, we still need to use ground couple GPR, maybe retrofitted on a push cart. But we also have the latest advancements of technology, like multi-channel GPR systems, that they can also be installed in a vehicle, but they can collect a lot more information. GPR is combined with other technologies to obtain more information and integrate that different or that multiple data. And GPR is also, there are already like a few standards. So it's been used for many years already, and there are multiple standards for different applications of GPR. Particularly of interest, we can use GPR for thickness evaluation, subsurface or utility mapping, bridge deck evaluation, river mapping, changes in construction. And there is another application that is still on the research stage, which is mapping air voids on newly constructed asphalt pavements. For example, for thickness evaluation, we can get with GPR a continuous thickness profile. We can also identify different types of pavement, for example, flexible or asphalt pavement compared to composite, that's asphalt on top of concrete. For example, you can scan large networks and you can present results in a graph fashion like this. This is a graph that includes a 40-mile segment with 3 lanes and a shoulder. This is particularly on the Atlantic City Expressway. So on one graph, you can get a continuous profile of your entire roadway. And the vertical graphs represent, or they represent ground truth cores that were taken on this project. So like I said, it can give you like a continuous profile of your roadway. Because we always collect with GPS coordinates, you can also georeference that data and put data on this type of graphs or maps, like Google Earth, for example. You can color code your data and get different colors for different thresholds, and show some ground truth samples, for example, like in this case, just to compare your data with those samples. It has been in use a lot, GPR, for subsurface utility mapping to identify utilities and subsurface anomalies, like, for example, potential voids or compromised areas. Also with the use of having multi-channel systems available, you can also obtain not just single profiles, you can also kind of obtain an X-ray of your roadway, no, and do like a tomographies from the top, no, which makes everything easier to interpret it and analyze, no. So, for example, this is one of the examples that you can get with this type of technologies with multi-channel GPR systems. Let me see if I can play the video. So we're looking at, from the top, it's like a movie showing the GPR reflection at different depths. And as you move from the top, you will see like different utilities crossing transversely and longitudinally, and at some angle will appear on the video. No? So this type of results you can obtain with multi-channel GPR systems. Go to the next. Also, because GPR, like I said, is always collected with GPS coordinates, we can export all the results georeference, like in Google Earth platforms or ArcGIS, or we can export it to AutoCAD and overlay on as-built. It can be used, also on forensic investigations, like we have done, for example, a few projects trying to detect railroad tracks or rail ties as well under the roadway. And GPR, for example, is a particularly great tool for that because it reflects all the energy at metal objects. So trying to find rail tracks buried on your pavement is a very nice application of GPR. It can be also used for bridge deck deterioration mapping, river detection, and measure the river cover depth. This is an important feature for bridge deck assessment. The type of result that is obtained when you do multiple passes of GPR is this type of color coding that you can differentiate areas that are deteriorated. Let's say you put red color usually, and identify areas that don't show any type of deterioration as green. So you can pinpoint the areas that need rehabilitation or maybe more in-depth testing. Like, for example, you could send just to do chain drag or verify your findings on only one area of this bridge. And GPR is also, or compares fairly well with other ground truth methods. Like in this case, it was compared with chain drag, and results were pretty much one-to-one. It's a very nice tool also for identify rivers in concrete, river, the alignment, whether it's a vertical river or horizontal river, and also to identify the river cover depths. No? This is particularly useful for the cases that we don't have as-built, like all concrete piers. We have had many projects like that there was no as-built, and we had to go there and do a complete GPR scanning to identify the river alignment and the river depth. No? It can also be used to identify changes of construction, like I said before, because steel is a perfect target for GPR. If you want to identify whether you have concrete under your asphalt pavement, it's a very nice tool. And with these multi-channel systems, it creates or it makes data collection more efficient. So you can scan really large areas within a very small time. No? This is one of the applications that is still on the research stage, but it is showing promising results. And this is to compare GPR with air voids on newly constructed flexible pavements. Results are usually same type of visual displayment on a color map or color image, showing in red, for example, areas with low density, high air voids. Like, for example, in this case, maybe the area that is showing low air voids is probably around a pavement joint that's showing the lower density. So this is something that is still on the being investigated by agencies and universities, but this is showing promising results based on the comparison with ground truth air voids in cores. Okay. Another type of NDT that is being used quite often and is this type of 3D laser cameras for roadway inspection. This type of cameras, I don't know if my pointer is working, but this type of cameras, what they do is they shoot a laser approximately 14 feet wide, and then you can collect data at 60 miles an hour, so you don't need to do any closure, any slowdown on the roadway. But with this type of cameras, what they do is they take or they obtain a 3D laser image of your pavement. With this type of cameras and software that comes with them, you can also extract all the surface defects like cracks, patches, rutting. And usually this type of cameras is integrated with other systems, you know, like front view video cameras to get the right-of-way image of the pavement, profilers to measure the ride quality. We can also integrate all these systems with ground-penetrating radar systems to measure the pavement thickness. So with one pass, you get a complete picture of the roadway. You know? Also, these 3D laser cameras, they automatically identify and classify pavement distresses. So this type of system and vehicles is being used by many agencies to do roadway assessment. This is just an example of a recently completed project by AID, this is Middlesex. So you can scan larger or large networks and do the analysis in a lot less time compared to before. And you can also color code and try to identify areas that need rehabilitation. And because it's a machine-based system, this type of cameras, they're safer and they're more objective compared to, for example, if you had to do the same inspection with engineers, no? Just visually assessing the pavement. This type of cameras, there is another version that is also used for rail inspection. It's the same type of camera, but it goes on a vehicle with rails. And in this case, the objective is to measure the rail condition and also the tie condition. No? There are other types of laser systems, like the one I'm showing here is a different type of laser, but this one is, instead of shooting laser down, it's like a 360 rotating laser. This is a specific type of device that is for tunnels. No? And this, for example, this particular device not only completes or obtains the laser image of a tunnel, but it's also it also includes thermal camera. So you are collecting at the same time thermal information from the surface of the tunnel and also a laser image of the tunnel. That image can be used to identify all the cracks, all the surface deficiencies, but with the thermal camera, we can also identify other types of deficiencies. For example, you can see on this image, there are 3 areas in this tunnel that they seem to be leaking, but when you look at the thermal profile, there is only one that is an active leak. The other 2 probably is just old leaks that they were sealed or they're not leaking anymore. This type of system, it can also provide this kind of going through a tunnel. It's more like a visual result of your, just to do like a go through the tunnel. It's not being used for analysis, but it gives a very nice representation of your tunnel. The same thing can be done with, instead of the laser camera, it can be done with the thermal camera. And visually, you can identify areas that, for example, dark blue will be probably associated with areas leaking inside your tunnel. So this type of representation and deliverable you can get with this type of system. This specifically or specially designed laser system that is for tunnels, we have been also using this on retaining walls. Is the same thing, but instead of looking at the entire profile, we just look at the data that is relevant, no? That will be the retaining wall itself. Same thing, we can combine or look at both laser image and thermal image at the same time and identify not only the surface cracks or surface deficiencies like spalling or river exposed, but we can also look at the thermal profile and, like the previous example, identify areas that are actively leaking or areas that are not leaking anymore. We just have the stain on the surface of the wall. Another type of laser technology that probably some of you know is LiDAR. LiDAR is a different type of, it's similar to the previous device, but this is less detailed. It collects less number of points, but it's more like a 3D laser. And this type of laser or LiDAR is used to create a point cloud, and then you can obtain different features, like, for example, measuring assets. No, this is the main objective of LiDAR, measuring assets, like, for example, traffic signs or markings, or, for example, to measure bridge clearance. No. Infrared thermography is another one of the rapid entity that is being used quite a bit. I mean, it's been used not only for on civil engineering applications, but also in medicine, electronics, or mechanical engineering. No? Mostly for civil engineering or for infrastructure assessment, the objective is to identify defects that we cannot see, like the previous cases that I showed with active leak points versus points that don't have any active leaking anymore. For example, on roadway sections, infrared is useful to identify areas of delamination of the bonding. Depending on the time of the day, these areas will look either cold or hot compared to the surrounding pavement. Like in this case, it's hard to see, but in this case you can see, oh, sorry. Like in this case, the areas that were probably previously identified, maybe through visual inspection or some sort of chain drag, they are seen as cold spots on the thermal footprint, on the thermal image. Infrared can be applied, can be used for bridge assessment. If you need to inspect bridge elements, usually we install a camera close to the bridge element that we need to inspect, but we don't need to be physically in contact with the bridge. We can set it far away and then identify areas that could be defects. Also on the bridge deck, we can put it on a vehicle and obtain data also at posted speeds. And like I said before, you can identify areas that are being that have delamination or debonding. UAVs or drones are also very popular these days because they can combine not only visual cameras, but they can also integrate thermal cameras. So it's very useful, especially to inspect areas with very or limited access, like bridge decks or tall bridge decks or underside of bridges that you will need like a UV50, UV60 track from the top. UAVs or drones are a perfect solution. Usually this type of testing is done by two people, the pilot and an assistant. And for example, in this case, we were testing a retaining wall, so the guys were just sitting there, flying the drone back and forth and scanning completely the retaining wall. Same type of result. You can obtain a high definition image of the surface of the element that you are investigating. You can also obtain the corresponding thermal image, and you can identify areas that could be associated with maybe some defects that you don't see. It can also be used for a building assessment, same principle, try to identify either cold spots or hot spots that could be associated with maybe some debonding or some water infiltration or leaking. And those are the main GPR, infrared, and laser systems. Those are like the main rapid tools for infrastructure assessment. There are other types of NDTs that are also being used that are very relevant, but they might not be that fast, but still it's worth mentioning them. Like, for example, falling weight deflectometer that is used to identify the structural capacity of pavements and the subgrades below, or skid testing devices that are used to measure pavement friction. Other type of devices that are more like in-depth are very slow, but they can get or they can give you like high-quality data, but on smaller areas. For example, are seismic devices like the PSPA that I'm showing on the left. We were testing on some concrete piers. Or ultrasonic tomography that is also used for concrete integrity or to identify voids below the surface. In summary, NDT methods, they have a wide range of applications for transportation infrastructure. There are a lot of NDTs that are already a state of the practice, but research is always developing. The new tools, new devices, new methodologies are being researched. So there's always more to come, but there are a lot of tools already that can be used for many different applications. Also, there are already many of these applications are followed by many standards. So we all do all this type of testing according to some standards like AASHTO or ESTM. Like I said before, because you don't need to have inspectors on the ground, it's a safer technology compared to traditional methods. However, it's important to know what are the limitations of each of the technologies that you want to use. No? So you need to know what it is used for and what it is not good for. No? So that is important for a selection of the right NDT tool. And sometimes, like I said before, I mean, a combination of the different NDTs gives you the best bang for the buck, no? Because you can, for example, in those type of integrated testing vehicles, with all those devices integrated, you can collect a lot of information with one pass, and it can be done very, very quick. No? Also, I mentioned that ground truth data is always needed, so collecting all this data is really valuable, but equally important is to do some sort of calibration or verification, but only on a limited case. No? And also, just worth mentioning that there is a nice web page from FHWA that they have manuals and they have like a selection tool based on your need. It will tell you what type of NDT is better suited for your problem. No? If you are looking, let's say, for pavement thickness, it will tell you that the best NDT that you can use is GPR, no? And followed by verification coordinate on small cases. No? And I think that concludes my presentation. And now you have any question, feel free, please.
If anyone has any questions, if you could please go to the microphone so the people from home can hear better.
What type of method can UAVs be used at for inspecting the pin and hanger assembly of the bridge?
Yeah,
Drones?
you can use it for the bridges or bridge elements or the bridge deck from underside or for retaining walls that have limited access.
All right.
So,
Okay.
so that's I think the best application for drones. I think that's it, Shane. Thank you so much.
Right. Yeah, thank you, Manuel. And thank you, everyone, for joining us. That concludes our breakout session.